Robots in space.
Hello everyone, I'm Mike DiVerde. I'm an aerospace engineer. Today I'm wearing my FA-18EF shirt. Super Hornet is a U.S. Navy supersonic fighter and attack aircraft. On the right photo, there's a label for the inlet duct. When I was a structural design engineer at Northrop, we designed, built, and flew the very first fiber-placed composite to ever fly. On today's episode of Robots in Space, I will discuss the NASA Messenger spacecraft, which investigated Mercury, and a recent research paper that hypothesizes the existence of a layer on that planet composed of diamond. Messenger stands for Mercury, Surface, Space Environment, Geochemistry, and Ranging. Messenger is a NASA-sponsored scientific investigation of the planet Mercury and the first space mission designed to orbit the planet closest to the Sun. The Messenger spacecraft launched on August 3, 2004 and inserted into orbit about Mercury on March 18, 2011. 7 years from launch to finally sliding into its orbit. After orbiting the planet for more than 4 years, the Messenger spacecraft impacted Mercury on April 30th, 2015. On the right is a true color image of Mercury, taken by Messenger. Note the quite dark color. This dark color is due to the abundant graphite, which is pure carbon. You know what else is pure carbon? Diamond. Here you see a diagram for the major spacecraft components and another for the scientific instruments. Note the sunshade, which is a ceramic cloth to help deflect the extreme environment near the Sun. Earth is 93 million miles from the Sun. Mercury is only 29 million miles from the Sun at nearest approach. Also notice the X-band phased array antenna, which made its first appearance on a deep space voyage. We will also discuss the Mercury laser altimeter, the gamma ray spectrometer, and the neutron spectrometer next. NASA's Goddard Space Flight Center developed the Mercury laser altimeter, MLA. MLA mapped Mercury's landforms and other surface characteristics using an infrared laser transmitter and a receiver that measured the round-trip time of the individual laser pulses to determine the planet's topography. The data was also used to track the planet's slight forced libration, a wobble around its spin axis, which told researchers about the state of Mercury's core. MLA data combined with radio science Doppler ranging was used to map the planet's gravitational field. MLA viewed the planet from up to 1,500 kilometers, which is about 930 miles away, with an accuracy of 30 centimeters, about 1 foot. The laser's transmitter, operating at a wavelength of 1,064 nanometers, delivered 8 pulses per second. The receiver consisted of 4 sapphire lenses mounted on beryllium structures, a photon counting detector, a time interval unit, and processing electronics. Gamma ray and neutron spectrometer packages separate gamma ray and neutron spectrometers to collect complementary data on elements that form Mercury's crust. The gamma ray spectrometer measured gamma rays emitted by the nuclei of atoms on Mercury's surface that are struck by cosmic rays. Each element has a signature emission, and the instrument looked for geologically important elements such as hydrogen, magnesium, silicon, oxygen, iron, titanium, sodium, and calcium. It also detected naturally radioactive elements such as potassium, thorium, and uranium. The neutron spectrometer mapped variations in the fast thermal and epithermal neutrons Mercury's surface emits when struck by cosmic rays. Fast neutrons shoot directly into space. Others collide with neighboring atoms in the crust before escaping. If a neutron collides with a light atom like hydrogen, it loses energy and is detected as a slow or thermal neutron. Scientists looked at the ratio of thermal to epithermal, slightly faster neutrons, across Mercury's surface to estimate the amount of hydrogen possibly locked up in water molecules and other elements. Measurements from MESSENGER's MLA instrument during the spacecraft's greater than 4-year orbital mission have mapped the topography of Mercury's northern hemisphere in great detail. The view shown here on the left is an interpolated shaded relief map of these data. The lowest regions are shown in purple, and the highest regions are shown in red. The difference in elevation between the lowest and highest regions shown here is roughly 10 kilometers. Among the prominent features visible here are the smooth northern volcanic plains and the enigmatic northern rise. The low-lying craters near the North Pole host radar-bright materials thought to be water ice. Despite the short distance to the Sun, the axis of Mercury is not tilted enough to expose the interior of the craters at the poles, providing perpetual darkness and extreme cold. On the right is a true color image of Mercury, which is remarkably dark, which is interpreted as abundant graphite, which is pure carbon. Now we'll watch a brief video that shows the mapping of the Mercury laser altimeter, accompanied by Jason Geringer's new composition entitled Mercury. Enjoy. Here we see a false color set of images of Mercury that shows the surface composition. The MASCS instrument was designed to study both the exosphere and the surface of Mercury. To learn more about minerals and surface processes in Mercury, the Visual and Infrared Spectrometer, VIRS, portion of MASCS collected single tracks of spectral surface measurements since MESSENGER entered orbit. The track coverage is extensive enough that the spectral properties of both broad terrains and small distinct features such as pyroclastic vents and fresh craters can be studied. To accentuate the geological context of the spectral measurements, The MACS data have been overlain on the MDIS monochrome mosaic. Here we see the low reflectance material, LRM, ejected from craters. Quoting from the research paper entitled Mercury's Low Reflectance Material, Evidence for Graphite Flotation in a Magma Ocean, targeted low-altitude thermal neutron measurements for 3 LRM-rich regions confirmed an enhancement of 1 to 3 weight percentage carbon over the global abundance, supporting the hypothesis that the darkening agent in LRM is carbon. Though seemingly unlikely on a terrestrial planet's surface, particularly one so close to the Sun, two explanations for carbon on Mercury's surface have been proposed. The first suggests that carbon could be exogenic, delivered gradually by comets over Mercury's history. The second suggests an endogenic origin, that any carbon that did not partition into the core of the planet would crystallize as graphite and would have floated to the surface, creating a primordial graphite flotation crust. Here we see a section through the planet. Quoting from the research paper, it has been suggested that Mercury differentiated through a magma ocean stage in which substantial heat and melting of the planet took place. Van der Kayden and McCubbin showed that the low FeO, iron oxide, content and limited density range of Mercurian melts prohibits nearly all rock-forming minerals from forming a primary flotation crust on Mercury, with the exception of graphite. And here they refer to figure 5. Furthermore, Mercury's shallow mantle results in a limited pressure and temperature profile that does not span into the diamond's stability field. Graphite is therefore the stable phase of elemental carbon throughout the silicate portion of Mercury, which is a primary prerequisite to the existence of a graphite flotation crust. Now we will discuss the primary research paper entitled A Diamond-Bearing Core Mantle Boundary on Mercury. So the themes of this research paper are: number 1, carbon speciation in Mercury's interior. The study reevaluates the forms of carbon present in Mercury's interior, considering high pressure temperature experiments, thermodynamic models, and recent geophysical models. 2, magma ocean and core formation. The research investigates the conditions under which Mercury's magma ocean and core formed, focusing on the role of sulfur and carbon. 3, graphite and diamond stability. The paper explores the stability of graphite and diamond in Mercury's magma ocean and core mantle boundary, CMB. 4, core crystallization. The study examines the crystallization process of Mercury's core and the potential formation of a diamond layer at the CMB. 5, geophysical models. The research uses updated geophysical models to reassess the pressure and temperature conditions at Mercury's CMB. So the conclusion that was made by the authors, it goes like this. The authors conclude that while it is statistically unlikely for diamond to have been stable in Mercury's magma ocean, the formation of a solid inner core could have led to the crystallization of diamond from the cooling molten core. This process may have resulted in the formation of a diamond layer at the core mantle boundary, which has likely grown thicker over time. The study suggests that Mercury's unique reduced conditions and carbon saturation in different reservoirs have contributed to this potential diamond layer. Quoting from the paper, abundant carbon was identified on Mercury by MESSENGER, which is interpreted as the remnant of a primordial graphite flotation crust, suggesting that the magma ocean and core were saturated in carbon. We reevaluate carbon speciation in Mercury's interior in light of the high pressure temperature experiments, thermodynamic models, and the most recent geophysical models of the internal structure of the planet. The formation of a solid inner core caused diamond to crystallize from the cooling molten core and formation of a diamond layer, becoming thicker with time. So an obvious question is, how deep would you need to dig on Mercury to hit this diamond layer? For that answer, we will now discuss another research paper entitled Gravity Evidence for a Heterogeneous Crust of Mercury. The study of the internal structure of Mercury is fundamental for understanding the formation and evolution of the planet and of the entire solar system. Mercury is constituted by a very large iron-rich core with a radius of about 2,000 kilometers, a 400-kilometer thick mantle made of iron poor and magnesium-rich silicates, and a silicate crust with an average thickness of 35 kilometers. The core is divided into a solid inner core with a radius between 1,000 and 1,500 kilometers, while the outer core is made up of convecting liquid of iron sulfide, which is also responsible for the magnetic field. Therefore, the answer appears that one would need to dig through about 435 kilometers of rock just to get to the diamonds. That is 270 miles of digging straight down. And that's to get to a material that can be made here on Earth in a factory. So here's my summary. The researchers did an excellent job of taking the data from the MESSENGER spacecraft as it orbited Mercury, determined what the elements were that were on the surface, found an overabundance of graphite, and evaluated how that graphite could have come to be on the surface of Mercury. And one of their conclusions was that the entire planet of Mercury had very high levels of carbon throughout, and under the certain pressure and temperature environment that is occurring in the core as the planet began to cool, some of that may have formed a diamond, and that those diamonds may have floated upwards, and once they got to the solidifying mantle section, created a diamond layer several kilometers thick. The problem is that you have to dig down almost 300 miles through rock just to get to the diamonds. Omni futurists